In the last video, we defined the Laplace transform of the Dirac delta function. And we said in order to see whether that definition was a good definition, we needed to see if it was useful. Okay. So I've got a differential equation up here, actually an initial value problem, that would correspond to a damped harmonic oscillator. I know it's damped because the y prime term, which involves the damping coefficient, is not 0. Okay. And the forcing function here is 2 copies of the Dirac delta function, where we're applying an impulse force at time 3. Okay, so let's solve this using Laplace transforms, and then we'll take a look at the solution we get and see if it seems reasonable. Okay. So I can take the Laplace transform of both sides. And because the Laplace transform is linear, I know I can just take the Laplace transform of each piece and I can factor out any constants. So I'm just going to do a little bit of side work for the Laplace transform of y double prime. Remember, that's the Laplace transform of the derivative of y prime. And what the Laplace transform does is have me multiply s by the Laplace transform of y prime and then subtract y prime at 0. Now, we were given that this was equal to 1. Okay. And then this is going to be s times the Laplace transform at y prime would be s times the Laplace transform of y minus y of 0, and then, of course, minus 1. Now, we were given that y of 0 was 0, so that just drops out. So we're going to get s squared Laplace transform of y minus 1. Each time I took the Laplace transform of a derivative, I should have mentioned I was using rule number 11. Okay, so we're getting s squared, the Laplace transform of y minus 1, plus 4 copies, oops, that's not a 4, 4 copies of the Laplace transform of y prime, which we just saw was s times the Laplace transform at y minus y of 0. And once again, that y of 0 is just 0. Okay. Plus 20 copies of the Laplace transform of y. And that's going to equal 2 copies. I can pull that constant through. And the Laplace transform of the Dirac delta function is just going to be e to the negative 3s. What formula is that? That is formula 10. Okay, excellent. So it was the Dirac delta function at 3, so it's e to the negative 3 times s. All right, so let's see. I think I'm just going to add this 1 over and recopy things a little bit neater here. So I've got s squared Laplace transform of y plus 4s Laplace transform of y plus 20 Laplace transform of y is going to equal 2e to the negative 3s plus 1. Just bumping that 1 over to this side. And then I can factor out the Laplace transform of y. That's multiplied by s squared plus 4s plus 20. And that's equal to 2e to the negative 3s plus 1. So we'll divide through by this, and the Laplace transform of y is 2e to the negative 3s over s squared plus 4s plus 20 plus 1 over s squared plus 4s plus 20. Excellent. So we've successfully taken the Laplace transform of both sides. Now we need to try to rewrite this to make it match one of our nifty formulas. So I need to look at this denominator here and see if it factors. I would factor it into linear factors and use partial fractions to write it as a sum of 2 pieces. This does not factor. Okay, I think that's fairly clear, but if you're not sure, try plugging into the quadratic formula. You'll get that there are no real roots. So instead, what I'm going to do is complete the square, because I want to try to make this look like s plus or minus a number squared plus a number. Okay, so I've got s squared plus 4s plus 20 I'm going to cut the 4 in half to get 2, square it to get 4. I want to add 4 and subtract 4. That way this factors now is s plus 2 quantity squared, and then plus 16. So that's how I'm going to be writing these denominators. Okay. So we'll have the Laplace transform of y is, I'm going to just write that 2e to the negative 3s off to the side, and that's times 1 over s plus 2 quantity squared plus 16, and then plus 1 over s plus 2 quantity squared plus 16. Okay, now, looks like the formulas we're going to be trying to match. Okay, here I've got, actually, you know, I think I'm going to keep that 2 there. Keep the 2 on top, but just factor out the e to the negative 3s. That's going to be formula 14. I'm hoping that this is the Laplace transform of some function that's being multiplied by e to the negative 3s. And by formula 14, that's going to introduce the Heaviside function at 3 when I take the inverse Laplace transform. Okay. Then these two, I've got a number on top of s plus a number squared plus a number. That's looking like formula, I had it a minute ago, formula 4. No, formula 3. Okay, so let me just write down formula 3 here on the board. It says that the Laplace transform of e to the at times sine omega t is going to be omega over s minus a squared plus omega squared. That's when s is bigger than a. But this is what I'm trying to match. Okay. So for both this part, which is then going to get multiplied by the Heaviside function, and this part, which will not get multiplied by the Heaviside function, I'm trying to use formula 3, and I want to figure out what's my a and what's my omega, and make sure that I actually make it match. Okay. So it looks like my a here is going to be negative 2, because s minus a negative 2 would be an s plus 2, and my omega is going to be 4. That way, omega squared will give me 16. So what I want to have on top is 4. Don't have that in either case, but that's okay. I'm going to multiply this one by 1 in the form of 4/4, and I'll multiply this one by 1 in the form of 2/2. Okay. That way, what we get is 1/2 e to the negative 3s times 4 over s plus 2 squared plus 16 plus 1/4 of 4 over s plus 2 squared plus 16. This is now a perfect match to the right-hand side of formula 3 here, with a equaling negative 2 and omega equaling 4. Okay, so at this point, we are ready to then take the inverse Laplace transforms. So y is going to be the inverse Laplace transform of 1/2 e to the negative 3t times 4 over s plus 2 squared plus 16 plus 1/4 times 4 over s plus 2 squared plus 16. Okay, so the inverse Laplace transform is linear, so I can take it one term at a time, and I can factor out constants. So I'm going to get 1/2. Now remember, this contributed by virtue of formula 14. I'm going to get the Heaviside function at 3. And then instead of just getting the inverse Laplace transform of this, I'm going to get the inverse Laplace transform evaluated at t minus 3. Okay. So we're going to have then the inverse Laplace transform would have been e to the a, we said was negative 2, but instead of t, it's t minus 3. And then sine omega t, with omega being 4, so sine of 4 times, again, in place of t, it's t minus 3. Okay. So formula 14 does two things. It introduces the heaviside function, and it has me evaluating the inverse Laplace transform of this at t minus 3 instead of 3. So it's introducing that horizontal shift. Okay. Plus then 1/4, and this would just be e to the negative 2t sine of 4t. No shift, no heaviside function, because I didn't have the factor of e to the negative 3t here. Okay. So that's my function y of t. Now, let's look at that and see whether this kind of sort of makes some sense. Okay. This piece right here is what we got because of the forcing function, which remember was impulse forcing using the direct delta function. It kind of makes sense that if you apply a very strong force at time 3, that's going to turn on a reaction at time 3. Okay. So until then, all we were getting was this. This was just the natural response to the associated homogeneous equation. Once we apply that force, that turns on the response to this. And look at what it's turning on. It's turning on an oscillating, a sine function, but that's oscillating between e to the negative 2, t minus 3, and the opposite of that. So there's some exponential decay. So if I look at that, it's turning on something like so. That kind of makes some sense to me. That at the moment I apply the force, it's going to have its biggest impact, and the impact doesn't completely go away, but it diminishes over time because I'm not reinforcing that force. I applied it, I'm done applying it, and so its effect dwindles as time continues. That does seem reasonable for the way a harmonic oscillator would react with impulse forcing. And I will tell you that other folks have confirmed that it is reasonable. Not just that it seems reasonable to me standing here without a harmonic oscillator to actually play around with an experiment, but people have done experiments with impulse forcing on harmonic oscillators, and this does turn out to be a pretty good model. Okay. So in this example, we looked at a damped harmonic oscillator with impulse forcing. What we'll do in the next video is we'll take a look at an undamped harmonic oscillator with impulse forcing and see what that gives us, and if that also seems to make sense, reinforcing the notion that this definition that we made for the Laplace transform of the direct delta function is actually a reasonable definition and turns some utter nonsense into something helpful. Really cool.